if I show you anything else from anybody else, I would pause because it's never edit. You guys all left, it was still recording, they all walked out. I cursed. So 5 minutes later, things still rolling. I said, I'm still trying to figure out how that highlight that did you hit clip or trim. It's like what that do in the next video. We want to make light years go basically years into miles. Convert years to miles, convert time into a distance. So a light year is not a time. A light year basically is a distance. That's a distance. That's a distance. We want to convert that distance into that distance using this space because a light year tells basically how far this light travels and what it's doing back. So we got to get rid of the years and be left with only miles. So what you would do is you would take your 65 years that it takes the light from Aldebaran to get to Earth, and we're going to multiply by the speed of light. 186,000. And that's going to give us the miles that we want for every 1 second. So that'll give us miles over seconds. It's years times miles over seconds. Right now, that would be our units. If this is all you did, you got whatever this equals. But the units, and that's what's important. This is what takes you into calculus. Your final answer, the units need to make sense. The units have to make sense. If you're dealing with a position, your position should just be a distance or a one-dimensional, feet, meters, centimeters, miles, kilometers, whatever it is. But if you're asked to find a velocity, then you better end up with a rate. Meters per second, miles per hour, kilometers per feet, kilometers per day. So we have that one. If you ask for acceleration, you better get time or units of distance per time squared. Acceleration due to gravity is feet per second squared. There's negative because it's coming down from the center. But that's a constant number. That's the if it's in meters, negative 9.8 meters per second squared. That's how fast every object is accelerating from the center. It's different on other planets or bodies because the masses of those bodies are different than the mass of Earth. How fast you accelerate towards the center of an object depends upon the mass of the two objects. However, so let's get rid of that miles. I'll take here years at the end because that years convert to seconds in years. I'm going to go along with the next unit of seconds is a minute. So since I want seconds to reduce, I want seconds on the top and I'm going to have minutes on the bottom. And 60 seconds to a minute. And then now I have the seconds, I have minutes up here. I want to get rid of minutes. And with our units of time down below, I know that minutes, the next unit of time we measure an hour. We have 60 minutes in every 1 hour. And the next unit of time above an hour would be a day, so I can reduce that hour unit of measure. Days would be in the denominator. And there's 24 hours in the day. And yeah, I know we have a leap year. The next unit of time after days would be years. Technically, our calendar is about 365.25 days a year. And that means every 4 years, we add an extra day of February. For a leap year. What does that basically entail? It's the calendar, because as we revolve around the sun goes around us. This is what the 1500 years. As we go around the sun, it takes 365, approximately 0.25 days to get around the sun. It's not a perfect circle. It's an elliptical orbit. So it takes a little longer to 0.5. If we didn't have that adjustment every 4 years for the calendar, eventually summer might be happening in December. Because the calendar wouldn't adjust to where our position with our hemispheres and what direction it goes in as you go around. That wouldn't make sense. We couldn't handle summer in December. But where's it in 365 days in 1 year? So now look at what we've got. The seconds divided by seconds, minutes divided by minutes, hours of days over days. And the numerator is years. In the numerator, the only unit of measure left is miles. In the denominator, all the units are reduced. We don't say the word cancel because canceling is when you have -5 plus +5, and that adds up and cancel out to 0. However, if you say the word cancel, I'm not going to have a problem. But technically, it reduces. There are some math professors around here. The real issue to say cancel. So all you do is put that. So here is the 84. Again, haven't checked one out or don't have one. We will be using this by extension. Oh, I forgot the 180. Miles per second. That is 3.812702.4. What does E14 mean? Exactly, but what does it stand for? What is it, math, you're going to the decimal 14 times to the right. But what is the name of that process? Scientific notation. It means times 10 times 10 to the 14th power. The reason why it goes e to the 14th is because there's not enough room to put the entire number. And there's not enough room to actually put times 10 to the 14th on the screen either. So on calculators, the exponential notation or scientific notation is 14, which is scientific notation. You see that and change 2 times 10 to the 14th power. So that means we're going to take 3.81 7024. And we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times. We fill in these empty loops with zeros, and we get 3, 8, 1, 2, 7, 0, 2, 4, and with 7 zeros. That's how many miles away all the bearings. That's why we say 65 acres. Hundreds, thousands, millions, billions, 381 trillion, 270 billion, 240 million years. Miles. This is actually some of the stuff. When you don't know the answer, a lot of times it's about converting what you're given into what you want. What do you have in you want? Convert reads into radians. Back into radians. Those kinds of things are what people want to memorize formulas. It's not about memorizing formulas, it's about understanding the concept. There's concept. It's not just memory. Memorize things, you forget. Understand. Anybody know the name of the man-made rocket, the space probe that we launched in the 70s, that is the farthest man-made object from the Earth? There are two of them. Is it Voyager 1 or is it Voyager 2? Perfect, because one of them is launched Earth. Voyager 1. So Voyager 1 has left our solar system. And that's what I was doing on my phone. Research. Voyager 1, according to the most recent trustworthy, everything on the internet is true. This was out of November 17th. About 14.5 billion miles away. Now, it was launched in 1977. Voyager 1 and Voyager 2 were launched in 1977, 16 days apart. At this time, Voyager 1 was traveling approximately 17 kpx, kilometers, of course, it's going to be kilometers, every second. The height, 186,000 miles every second versus, hey, look it up, man. We got something going 17 kilometers every second. That's super cool. How long would it take Voyager 1 to reach a distance about America? Well, I'm not going to have to do the calculation, right? We'll put up some numbers. 100 years, 400 years, 500 years, 1,000 years, 10,000 years, 50,000 years, 100,000 years, 500,000 years, a million years. Hello, I should not take, I'm gonna break that. I need to just keep on going. Okay? 5 million. It never will because the board will pick it up. I don't know. Anybody guess 100? Anybody root for 400? Anybody root for 500? Anybody root for 1,000? Anybody root for 10,000? Anybody root for 50,000? I want. Anybody root for 100,000? What? Anybody root for 500,000? Anybody root for about 1 million? What? 5 million. Got 3. Anybody root for 10 million? Got 1. Okay. Well, according to my estimation calculations, I came up with 1,144,527.585. And 17 wrong. A million years to go. Yeah, you know, your lifetime, you might get a chance to go to space, but maybe in your grandchildren's lifetime, they might get a chance to go to the moon. The Artemis project is supposed to happen this decade. The Artemis NASA is going to go back to the moon. Mars is going to be after that. Light areas, Mars. Colonization, oh yeah, that's right. All there. All there is the Taurus in Taurus. It's the bull bloodshot eye. So here's Orion. And if you take Orion's belt, Orion archer, MW rifle, and if you take the belt of Orion, it's almost a straight shot to the whole there. You drive as far as the night sky in a couple of nights. reason why they call this the forest right there. Interestingly, in about 2 million years, and that's the big proof. Now we want to face what's happening in 2 million years. National will have some fantastic all of it. Now compare the size, all of them versus the size of our sun. Why do they call it the red eye of the bull? Because it's a red star. Now remember, what we see in the night sky happened 65 years ago, so we are looking at the past. Every time you look into the sun time machine, when you look at the stars, time machine, you're always looking at the past. Because that light is not there. It's not exactly what it is. Which is always interesting to me because whenever we look at objects, engineers, mathematicians, NASA people, when they plot forces to say a comet and land on a comet, when they're looking at where that comet is is not where it is when they're seeing it. But they plot the trajectory of where that comet is going to be, and then they are able to program whatever program in about 12 or 18 months from now to meet up with that comet or whatever it's going to be, when that comet will be there. And when. That's what kind of boils my brain. It says it's the orangish color of K5 giant star. 153 times brighter than our sun. Surface temperature is lower because it's a red star. 4,000 Kelvin. Or about 3,700 degrees Celsius, 6,700 degrees Fahrenheit. Our sun is about 10,000 degrees Fahrenheit. All the variables is an erratic variable with a minor variation. Too small to the eye. We also have a small big companion star and M type. Light day away. In other words, light from all variables we can try to see contrast the light 8 minutes. So our sun is 8 light minutes. Hopefully, I can put forward the I don't know if you ever wondered, and all I'm going to do is just give you an idea of where all this is. But what we do here, this is all just the difference between the map that we do in algebra, trig, math, whatever. The map that we do is called a stagnant system. It's stagnant, it's not. It's like you take a snapshot, do the math on that picture, versus when you get to calculus. Calculus is a dynamic system. Things are in motion. And you're trying to do that while everything is continually moving, while things are changing. When we do slope, the most important word in mathematics is guiding word, all of that. Slope is a rate of change. Kilometers per second, miles per hour, that's a slope. It's a rate of change between distance. That's what Isaac Newton was working with when he was discovering calculus. He wanted to know, how can I find the instantaneous velocity of an object? How fast is something move at exactly 3 seconds? All you can do with slope is work out. Let's figure out the slope between 2 different time values. You have, because in slope, you have a denominator. In the denominator, you subtract the x coordinates. x2 minus x1. So you have to have 2 different ordered pairs. If you want 1 point at one time, then x2 and x1 are the same number. And when you subtract them, you have 0 in the denominator and you can't divide it. So you can't do the slope at one moment in time. You decide, all right, you can't do it at exactly 1 moment in time, but what I'm going to do is I'm going to take these 2 times and I'm going to let them get infinitely close to each other. So if I wanted to find what is the instantaneous velocity of 3 seconds, I'm going to let my variable t get infinitely close to 3 seconds. Okay, so from both sides. So let's go from the north left to the right. Here's 3. What's the velocity in 2 seconds? Between 2 and 3 seconds. 2.5 seconds. 2.8 seconds. 2.9 seconds. 2.99. 2.99. 2.999. 2.9999. And what he discovered is as you let one t approach that other t, you let t approach the seconds, you actually get the slope at exactly that moment in time. Instantaneous value. And that's what calculus is. That's called the derivative, differentiation. That's what. But it's about working on an infinitesimal scale. When you do area in geometry, we can take the area of any polygon, slice it up into rectangles, slice it up into triangles. We can do polygons like nobody's business because we know area formulas. We can do a circle, area of a circle, pi r squared. But when you have a parabola, that's not a circle, it's a curve. So what's the area under a parabola? Well, we don't have a formula for that because it changes. Newton says, all right, if I slice up underneath the parabola into a rectangle, and then I slice the rectangles up into more rectangles, and slice those rectangles up into more rectangles, until I have an infinite number of little tiny slivers of rectangles that add up the area of all those rectangles. I'll have exactly the area under that curve. But it's that simple concept of taking something to infinity. That's the difference between working in a standard system and something that we couldn't do before the 1700s. After the 1700s, the video that we watched, how things are always changing. We're studying for careers that don't even exist. Different types of things, all of a sudden, careers that never existed. How many aerospace engineers were there in 1950? Now there's aerospace engineers that can't get a job. Well, technically, there's private sector. Private sector. Got my email, I hope, about access to the playlist where I posted the video on. I know a couple of you actually watched it. The video from Monday's class, right? At the end of class, I get an email from Zoom. The video is ready. I download the video from Zoom. Then I upload it up to YouTube. As soon as it's done, upload it on YouTube. I email the entire class from Canvas. Okay, so you get email, so you can just click the link on Canvas and you go straight to the video. That way you don't have to open up YouTube, find the playlist, and then click on the video for the class. What day was it? I'll send you the video that day so you have access to it. Now, here's what I want to make sure. I don't like, but I have so many different classes that don't know what I said to everybody. One more. When you email do not email me in Canvas. Did I say this? Personal account to my Outlook account, so that way I don't have to try to get your extract your emails out of a whole bunch of other Canvas. Especially if you get a reply and it's embedded within the email or something. All right. But I will post today. I handed it out to you. I did not post the assignment. This. Everybody have this? Anybody need today? So you can watch this YouTube when you get today's YouTube link. You can click on Mondays from the yeah. You can see what we did with the syllabus. Covers everything, but that's the assignment sheet and syllabus. And you know, no big deal because hey, don't forget, no school Monday. You show up on Monday, you're going to be alone. So that's the assignment that we're going to start working on 5.1. And like I said, I will allow you, I don't mind if you know. Somebody did Amazon for math creating that their book for free. I don't know what strings they pulled, but I know there's also a website where you can download the book for free. I don't know what that website is, though. I don't want to know because I don't want the authors and the publishers coming after me saying that, hey, I'm only going to be recording. I don't want the publishers coming after me, but what you guys decide to share amongst yourself. But so what I'm using up here, PDF, that's you can have it on your computer. Any questions? So angles. You know what an angle is? An angle is the union of two rays joined together at their endpoints. The angle is the rays themselves, not the amount of opening. That's the angle of opening, but the angle itself is the physical ray and ray. You have an initial side and you have a terminal side. And there's a direction of opening for an angle. I highly suggest, recommend, hope you invest in something, a very, very important piece of technology that's been around for about 5,000 years. Oh, straight edge. Because you will be But even doing trigonometry nicely is to make this a picture. And when you make this a pictures, the better, the more you can draw them with straight edges. Draw them with, like you give a darn. Sorry, you give a shit. When we get to the very end of the class, you're going to be doing some navigation, some plotting, some, basically some. What is the distance if this angle of ship leaves on a heading of 017 for 450 miles per hour for 1.5 hours, and then it turns on a heading of 183 for 3 hours at a velocity or speed of 172 miles per hour. What is the distance that ship is from port? If you don't draw a decent nice picture, then what you draw by freehand, your brain is not going to interpret your answers that are coming out from your work. The picture looks like that's a 50-degree angle, but your answer coming out at 137. And your brain's going to blow a circuit because what you see is not what you're getting. You do it wrong. You started it because you didn't draw a decent. Take the care to draw a decent picture first. And that's the key. Going to drive you nuts. Ask them to draw a picture. Draw a picture. Sometimes I tell you draw a picture. Straight edge. They're also called rules. On angle, you have what we call the initial ray. So ray has an end point, and then there is some point along the ray that tells you what direction it is. And then, if this is the initial ray, then you have the direction of opening that we more than likely will always open counterclockwise. And you'll see what I'm talking about. So we will open counterclockwise for a reason. So you take another ray, starting at that end point, go to that point. The end point that they have in common is called the vertex of the angle. The terminal ray is where the amount of opening stops. It's not where the angle is going to die. So, that's a basic anatomy breakdown of what an angle is at this level. This side, terminal side, and more than likely, we're going to be drawing it on the next y-axis. So here's what I'm going to be giving you guys gradually as we go through the semester. We're slowly going to be building what we call a unit circuit. Right now, I'm not going to do these two today because we have very specific measurements. We're just going to draw our XY axis by freehand. So when we do things in this class, the vertex of these angles will happen here at the origin of the XY axis. The initial side will be the positive x-axis. And then the terminal side will be some opening as we rotate counterclockwise. Like so. In geometry, you study acute angles. You study right angles, 90 degrees. Acute less than 90. You study obtuse angles, greater than 90 but less than 180. And you study straight angles, which is exactly 180 degrees. In this class, you can have lots of angles. The initial side. And then we pick our opening and open all the way in here. Into the third quadrant. We don't have a special name for it, but it's not an obtuse angle because it's more than 180 degrees. So if this cutoff is 180, and you know, to go all the way around, that would be a 180 and another one. That would be 360 degrees to go all the way around. How big is this angle? What does it have to be in between? It can't be small, it can't be bigger than, but it has to be greater. Remember this. 270 and 180. The variable that we use to label angles in trig, the favorite variable that you will get to know is theta. We don't have the Greek fraternal sorority system here at the junior college level. But when you go into a 4-year college, you know, going to grad, going to sorority, you get to learn the Greek alphabet. We use the Greek alphabets to label angle measurements. Okay. Theta, phi, alpha, beta, those are a lot of the different angles because usually when you just label points, we use capital letters. That's angle ABC or angle CBA or angle B. But if I want to just call this, hey, this is angle theta, then we can just call that's angle theta. Okay. So theta is going to be used quite a bit more often than video. When we get later on, we start working with triangles. We label our triangles. Vertex Q, there's R, triangle QRT. So we might say, what is the measure of angle R? So we wouldn't pull out the Greek letters because now we're working in the triangle. But this angle theta would have to be bigger than 180 degrees, but less than 270 degrees. Now you could say it has to be less than 360, but more specifically because when you look at the 4 quadrants, it's giving up into 4 right angles. If the whole circle is 360, then here's 90 degrees, that's a right angle, another 90, here's another 90, and there's another 90 all the way around 4 times is 360. So this one all the way 3 times around, that would be at 270 degrees. So if you're in quadrant 3, you have an angle in between 180 and 270. If you're in quadrant 4, there's between 270 and 360. But you can have an angle like this. So the initial ray is filled, the positive x-axis, the terminal ray is in quadrant 2, but it opens a full revolution. Kind of like Pete Townsend playing the guitar. I should do that. We're going to deal with a lot of my grunts and drums and pain. I have that back, and I know this shoulder's happening. Writing right now, the reason why it's so bad, I feel my shoulder flipping the entire time, and if I try, I can't help it. I can't pull it over. No, I'm kidding. That's hard to get off when you do it almost 10 years. There are doctors that give you that stuff, and they just, all they do is keep writing. Thank goodness I wasn't addicted to it, but it was difficult to stop. I had to do your brain says your body hurts more, so it can get that medication that I got. Amazing what can have an addictive background. You know, that makes you. So you see how big of that angle has to do. Again, no reaction out of you guys, man. It's like I'm talking to the black screen very Zoom. You know what? I took, you know, compensation like really evil. Oh, once I dated Brooke Shields went in the 70s. I went through her high school forum. Oh, Madonna and I. Oh, yeah, I went through that. What was the first one? 450, 540, yeah. Because 90, 90, 360, 360 plus 90, 450 up here. And then another will be 540. So this is in between 450, 540. If I said it wasn't exactly an angle, if I said theta was equal to, oh, let's say 520 degrees. Part of the homework you're going to see is going to ask you for name at least 2 coterminal angles. Coterminal angles to the given angle. Now, technically, I'll tell you, there's an infinite number of answers. But I'm going to tell you, here's what I want. I want a coterminal angle that is in between 0 degrees and 360 degrees, And something we haven't talked about yet, but I'm going to talk about it now. 0 degrees and negative 360 degrees. So, coterminal. The key to mathematics, language, translation. When you learn a language, it's about translation. I don't know if Google Translate is going to help, but I don't think we have a math of English. They have a thing on one, but they don't have math. Co, that means at the same time. We can cohabitate. We're living together in the same place, together at the same time, sharing something. Okay. Okay. We're making the payments at the same time. We're sharing that. We have some joint thing together. Co-terminal. They share the same terminal side. So in geometry, we learned about colinear, points that were on the same line. Coplanar, lines that were on the same plane. Okay. Now we're talking about coterminal, angles that share the same terminal angle. So we need to stay between 0 and 360. So from 0 to 360. So that's going in the positive direction right here. You can't go past, all the way back around. You gotta go just to here. That's as far as you can go. Well, that's 0, start at 0, and open up to where that terminal ray is, and that terminal side is. And what would the measure of that angle be that has the same terminal side as the 160? Here's a couple of ways you can get it. I'm a visual person. I like to see pictures. Sometimes I need to see pictures. One thing I know that I can't do is when students ask a question like number 17, and they start reading the problem. Stop. All you hear is long, like Charlie Brown's class, long. I can't understand it and write at the same time because it's not making the connection. I need to see what I'm working with in order to do it. That's why I have to draw pictures. Helps me put the pieces of the puzzle together. So when I do problems like this, I usually draw a picture, even though I know I could just use, I don't have to draw the picture, I can just use that. You know that we have numbers that will always be there. As you go around the XY axis, you go around and around. You got 0 degrees, go up, you got 90 degrees, go up here, 180, you got 270 there, that will be at 360. If you keep going around, this is also 450 once you make your second trip around the circle. 540 degrees, 630 degrees, and 2 complete circles, 360 plus another 360, we finish up here at 720 degrees. And if you kept on going, 720, that's 810, 900 degrees, 990, 1080. Revolutions. So visually, what I know is that this is always going to be 180, 540, 900, 900, so on. Okay. So that's 540 and that's 520. I know this angle right there is 20 degrees. So that little sliver on this side is 20. and that 540 is also a 180, then this would be a 160 because 180 take away that 20 would give you a 160. When I see it. But it's also just this. Here's that 540. So what do we want? We want just between 0 to 180. But technically, we just want this. So you gotta go from that 520. What you're gonna do is you're gonna subtract from that 520 a revolution. You subtract one revolution and it takes you to where you are between 0 and 360. So that gives us 150. Now, what about the negative line? Well, again, when we're talking about angles in this class, we're going to be always using called standard position. Where the vertex at the origin and the initial side is positive x-axis. Vertex, initial side, positive x-axis. When you go counterclockwise, that is a positive angle. When you go counterclockwise, it's a positive angle. Reason, I'm making this up. I don't know if it's the actual reason. I never actually looked into it. This is the one that makes the most sense for me. The quadrants. When you have an XY axis, the quadrants are going to make 4 quadrants. In this quadrant, x's are positive and the y's are positive. We label this one quadrant 1. And when you label quadrants, you have to use Roman numerals. The reason why is because your x's and y's and ordered pairs are going to be used. So you don't want to get your label in a quadrant. You don't want to get confused with the other numbers on the x and y axis or any of pairs. Oh, by the way, if these are Roman numerals, what is nothing? Or Washington numbers? Indo-Arabic numbers. Mathematician by the name of Leonardo Pisa. Leonardo da Fibonacci in the year 1000 on the Mediterranean. He wrote the first algebra book for Europe. Algebra was discovered about 700 in the Middle East. That's where algebra was developed. The shipping lines that happened in the one zone, that's 700 to 1000, he was working, and that's where that math would start coming into play. And he said, now, their number system makes a lot more sense than they're using Greek letters. Well, this makes a lot more sense than what we're doing. Let's look at that over. It's not like, you know, it happens overnight. Somebody has an idea and discussion. That one took over, you know, 300 or 400 years ago, but you know, now we have more organized. But we do everything. And then the next quadrant is quadrant 2. We go counterclockwise. This is quadrant 3. This is quadrant 4. And your quadrants are going to have a real importance to them. What quadrant is that angle going to be in? What's going on in that quadrant? Who's positive? Who's negative? What makes the difference? If you don't know what quadrant it is, that's when I tell students draw a picture. Did you draw the finger on the right quadrant? Well, I just do a triangle. I just put it on an X by X. That's what we're trying to figure out. That will also help the picture. Now, complaining about things that I'm complaining about, like an equal, starting down, starting early, hopefully, if I get you tired of me saying it now, and maybe you just do it all the time. Or it's self-fulfilling prophecy, like it's complaining about it now, you're just going to do it. Or you plant the seed. So a negative angle goes clockwise. So if we open the angle into quadrant 4, this is 0. This going in this direction would be negative 90 degrees. Because it's open counterclockwise instead. Or basically go down, open up. Or we're sitting. That was that in my all down there. You see the thing Homer and Vince Street called the thing, basically show the thing Homer. Shows low, everybody loves it, so low steals it, calls it the thing low. Corporate finds out about it, corporate's giving them a whole bunch of Homer's angry about low. So in about 2-minute segment, you just all of his kids and Mark, everything you hear is just my granddaughter, life. We got to pick our own name, push to the fall. So my daughter-in-law's parents went with Nana and Grandma. I went with Pops. Under Pops. My wife was going with Oma, which is German descent. German. That's more Swiss Norwegian than German. I can say Oma. Oh, no. So I did tell my wife last week. I think that's too. I don't think my car. So this would be, I don't know, maybe like negative 60 degrees. If we go to quadrant 3, now we're looking at negative 128 degrees. Negative 180, negative 270, negative 360, negative 450, negative 540, and so on. Negative 630, negative 720, and so on. So this angle over here that opens clockwise and terminates there, is now going past -90, -180, which is right there. Another extra 20 degrees, but in the negative direction, so another 20 degrees in the negative direction, -200 degrees. So find two coterminal angles, one between 0 and 360, and one between -0 and -360. This one is 160 degrees, and this one is -200. How can I get that without drawing the picture? Well, you're at 520. You took away a rotation, and that's how you got the 160 degrees. So if we're at 160, right here, at the 160 mark, all you have to do is take away 360 to get right back to that same spot. Take away another 360. Positive 160 minus 360 is -200 degrees. Keep subtracting 360 degrees. Then what this is going to evolve into where the head is, up and that up. How do you measure angles in other measurements besides just degrees? Degrees are not the only way to measure. They're great when you're doing triangles, because, or polygons, because that. Triangle, all three angles happen at 180 degrees. Works, it makes sense. If you have quadrilateral, 360 degrees. Pentagon, 540, there's more meters. And we work with degrees. But when we want to graph trig functions, working with degrees doesn't really help. When you want to graph a sine curve, it takes 360 degrees for a sine curve to complete one full cycle, one full oscillation. The biggest value of sine can equal 1. The smallest it equals is negative. So the range of sine goes from -1 up to positive. That's it. 1, -1. That's the y value. The domain. If your scale, the x scale and the y scale, if you're going to have them be the same, when you go to graph, so the y-axis is the value of what sine or cosine is equal. So if I make that positive 1 and this negative 1, then this distance would have to be 1 degree. And you have to go all the way, probably, I don't know, way over there to 360 total degrees to keep the same scale, where this distance is 1, that's 1 in between. So that's not going to be easy. If your calculator's in the wrong mode, your graph's going to, it's not going to make sense. So there's another way to measure angle, and it's based upon surface. And this is not part of 5.1. This is just getting this point. I don't know if everybody has their book yet. So I always spend the first week kind of getting the language. But somebody, I don't even know who, but somebody came up with this idea. When you have a circle, no matter how big that circle might be, and you have a central angle, diagram. Back in the, 2.5. They didn't have compasses. So to make angles, they use a straight edge and straight. You want to draw a perfect circle? Just use a straight. 1 point, and then you want to make congruent angles? Use a straight edge and use. Remember, they didn't have paper pieces on the property. The length of the radius, right? No matter how big the circle is, no matter how big the circle is, if I take the length of this radius and then wrap it, that length of radius around the curvature of the circle. So the length of the radius is now the same distance as the arc, the length of the arc. So in other words, here's the length of the radius. The arc is also, if that's 3 centimeters, this is 3 centimeters. So this would also be the arc. Because it's a radius, circle. This amount of opening right here, okay. Watch what happens when I do over here. Granted, my circles aren't perfect. Not easy. Oh. Now, what is that saying? I know that. That's fact. That's really fact. But the amount of opening right there, no matter how big that circle is, it can look about the same. Now, the bigger the circle, the bigger the radius, which means the bigger the radius, the larger the arc. The ratio between the radius and the arcs will always be the same. So the measure of that central angle, that's a radius, that's the same length. The measure of that central angle is the same in any of those circles. And that's how they came up with the idea of this right here. The definition of what one radius, the amount of opening of the central angle if the arc length is equal to the radius of the circle. The amount of opening of the central angle if the arc length, the distance along the circle, is the same as the radius of the circle. That angle is now 1 radian as a measure of the angle. Now here's the nice thing. Radians don't have an actual units. Okay, basically it's this. In radians, theta is equal to the arc length. Now we use S as the variable of arc length. Then R is the radius. So theta in radians is equal to the arc length S divided by the length of the radius. How many radii can I fit around the arc? If I can put 2 radii There's a radius length and there's another radius length. Then this angle that I just made is equal to 2 radii. Oh. Because there's 2 radii that I can fit around that arc. If I can fit 3 radii around the curvature, then that's 3 radii of it. And that's how you measure an angle in radius. Back to the beginning of today, unit or dimensional analysis. The length of the arc is a distance. The length of the arc would be inches, centimeters, okay? Whatever, feet. The radius of the distance, inches, centimeters, feet, whatever. So if this was 3 centimeters, and let's just say that this was 3.6 centimeters. Then this measurement, theta, would equal 3.6 centimeters divided by 3 centimeters. Theta will equal 1.2. And there's no units because centimeters reduces. It's just moving. You ain't got no units. Now we call it radians. We call it radians because we want to make sure that we know we just want to measure an angle. We want to know what does it represent. But radians is not a unit. Radians is just, hey, we're talking about an angle. It's not necessarily. So remember, it's 360 degrees in the entire circle. What is this called in the circle? We start here and go all the way around, and what's this called? Well, what is the circle? What? The circumference of the circle. Okay? The distance around, that's the circumference. Circumference is equal to 2 pi r. Right? So if you had an angle like this, theta, which is equal to the arc length divided by the radius, the arc length is the entire circumference. So 2 pi r divided by the radius, and those 2 radii reduce. This angle for the whole circle is 2 pi always. So an entire circle is 2 pi radius all the time, every time. But a whole circle all the time, every time is 360 degrees. Which means the conversion, 360 degrees, is converted into radians as 2 pi. Just like 4 equal 1, 4 inches equal 1 foot. That's not the number you want. This will be a happy number. 180 degrees is just 1 pi in radius. We'll pick up there next Wednesday. What I need from you is make sure you gotta take those steps. Make sure you get your textbook if you haven't. If you want to take pictures of the homework, I will put it up here in a minute. If you want to just take pictures of the book, you can do that as well. But make sure you get your homework. At least take a look at it. But I just kind of gave up most of the ideas of chapter 5.1, 5.2, 5.3, kind of jumbled together. We will get more direct on Wednesday. All right. Roger Burns? Roger? Josh, say hi. Aldo? Marcelino? Yep. Vincent? Brennan? Daniela? I can sing Daniela. Daniela? Isaiah? Candace? And Chris? All right, you guys. Have a great weekend. Stay safe.